Hello and welcome to this special edition of C++ Weekly. I am your host, Jason Turner. I'm available for code reviews, contracting, and on-site training. In this episode, I would like to take a moment to discuss Apple's announcement of macOS Big Sur, its move from x86 to ARM64 for its desktop environment, and what that means. Now, I'm doing this episode because I've seen a few people say that this can't possibly result in good performance, and we're going to do an analysis of that and see exactly what the implications may or may not be for users of macOS who are moving to the new hardware. So as you can see here, this new operating system is designed to take advantage of Apple-designed ARM processors. Now, currently, like I said, they're using x86 64-based processors. These are completely different process architecture. They were developed independently, and both have been around for quite a while. Now, the interesting thing here is that Apple has announced that you will be able to run existing programs on your new ARM-based processor. So if you have a brand new system, you'll be able to run older applications. And this being two completely different architectures leads into all sorts of questions about emulation and what the implications for performance are. So we have this project here called Rosetta, and this is let's look at here, this is a binary translator. Now you'll note that there are two different versions listed. There is one that is PowerPC binary translator, and there's one that is an Intel binary translator. We'll get back to this older version in a moment, and right now we're going to focus on this one, Rosetta 2. So as I mentioned earlier, this is coming with macOS Big Sur, and it is to aid Apple's transition to ARM processors. So let's just try to dissect this for just a moment, what this looks like. Now, I'm going to use a Compiler Explorer background here for the moment, and I'll be coming back to this. We're not going to write any code here, but it kind of just gives me a big white space to work on. Now let's think about how a program normally executes. It's got some instruction, some instruction, some instruction, some instruction. It's executing CPU instructions. And then it makes a function call. And I put the semicolon after it because I'm used to programming in C and C++ style languages. And then it's going to execute a few more instructions, This function call right here is probably an operating system function call or a system library or something like that. So let's keep that in mind. But we need to deal with these, the before and after instructions. So if we are coming along and we've got this block of x86 64 instructions, and then we need to run some sort of translation or emulation or something on them, and we convert that to ARM 64, shall we say. And we've done this execution now, and then we come to function call. We can call that, and that's going to be just the same performance as if we had called it natively, because this function call, now being an operating system function call, or an OS level API or something like that, is going to be fast. It's going to be a native speed thing. And then we have to come back down here, and we have to do some sort of translation on our x86 64 to ARM. Now, this translation layer, this can be what? We can deal with many different things here. This can be recompilation. It can be emulation. It can be JIT, that's just in time recompilation, and this is the kind of thing that we see when we're doing something like running code on a JVM and then that goes to native code. As the code gets executed, it gets updated. That looks like JVM here. So these things are, in general, let's say, fairly solved problems here. We know how to do emulation, we know how to do JIT, we know how to do recompilation, but you still then ask the question of, well, what's the performance implications here? And one of the questions that we have to ask ourselves is, what exactly does function call represent? What is this function call? Now let's think about, like, if we are, say, in a modern word processing application or something like that. So if we're in a word processing application, then we're going to be doing things that are like what? Like calculating string lengths and doing Unicode. But even those things are probably going to be operating system calls. But even if they aren't, even if they're things that are natively compiled in here, and then let's just assume that these are things that have to be emulated calls. And then we're going to get to something that's going to be like draw widget, something like this, something that's going to be pretty high level. We're making an operating system call, and this is going to do a lot. This draw widget thing, or draw window, draw frame, whatever, it's going to draw your window, it's going to put in all of the controls, it's going to write out the text here. We've got all kinds of things that need to happen. We're doing font rendering. And so all of this now becomes something like a word processor, as an example, and we'll get to that more in a moment. This is going to be at least, well, not as least, but it's going to be pretty much as good as running just natively, as if the program were always written for ARM in the first place. And like I said before, we can see that this idea really isn't very new. The first example that I am personally aware of, and I'm sure this is not the earliest example because IBM has been doing things like supporting old versions of their hardware through emulation layers and whatever for a very, very long time for their large corporate customers. But let's just consider Palm OS. Now, I did some Palm OS development back in 2000, 2003, 4 era. I played with Palm OS development. It was a hobby of mine. And I actually sold an app for a while, but that's kind of irrelevant at the moment. Now, what we'll notice is this says platform ARM architecture here. That's not entirely accurate. If we go back to the original Palm devices, what we will see is that the original Palm Pilot was in fact an MC68328 Dragon Ball Motorola processor. And for those of you who don't know what that is, the Dragon Ball is in fact a 68,000. This is a processor that should be familiar to many of us, and it is in devices including the original Macintosh. Some version of the 68,000 was in the original Macintosh, and it was also in the original Palm Pilot released in 1996. So let's get back to Palm OS and what this means for our conversation at the moment. If we look here at Palm OS 5 Garnet, this was the first version to support ARM devices. This is starting to sound awfully familiar. And applications, this is the key, applications written for the prior OS versions use the older Dragon Ball 68K instruction set and are supported with the Palm application compatibility environment, PACE. This is an emulator, it says. So this is doing emulation. This isn't doing dynamic recompilation. It is loading the code that was written in 68K, emulating it to ARM, or emulating the 68K on an ARM, that is. So what we then see here is this little note. Palm OS applications usually run faster on ARM devices than on previous generation hardware. Now they are able to use a much faster processor, much more efficient processor than they were able to on the older Dragon Ball 68K systems. To the point that you didn't even very rarely develop code natively for the ARM. You continued to develop code for this old 68K instruction set and just trust that everything would run as expected through this Palm application compatibility environment emulation layer. And if you really needed high performance code, you would do this in this case of an armlet. So they really reversed things here. They expected us to still write 68K code, and we would run this for however long we wanted to, and we would make these OS calls, and that's where all of the heavy lifting was done anyhow, and the OS calls are written in ARM, natively for the ARM, and then if we really, really needed to, we could call an armlet. And then we could come back in and keep executing our 68K code. That's how they expected us to work, and it did work actually. No one complained about things being too slow on the new devices, and I apologize. This is a little hard to read, but it seemed like a thing to do while I was writing it out here. Okay, so that's one example that goes back to 2002. So this was 18 years ago. I promised that I would come back to Rosetta here, and I would come back to this original version that was PowerPC binary translation. Indeed, this is not the first time that Apple has done this. They did PowerPC to x86. Now, it was originally 32-bit, and they had this translation layer, this thing called Rosetta, back in 2006. So now this is the second major one that I am personally familiar with to some extent. I never wrote code on these devices, but I remember when all this news came out and we had the exact same questions back then. Oh no, can it have the performance that we want it to have? Well, this is already the second time that we were doing it then in 2006 in a major platform, and now we're coming up to the third kind. The second time that Apple has done this, third that I am directly familiar with. Now, there's a key part here, two key parts that I would like to draw attention to. With the original Rosetta, it could translate G3, G4, and AltiVec instructions. It could not translate G5 instructions. So if your application was written for G5 specific instruction sets, then you would have to recompile your application so that it could work. Now, according to Apple, applications with heavy user interaction but low computational needs, such as word processors, are well suited to translation via Rosetta. Now, the world has changed a little bit more. Now we do less and less work with the CPU in many applications, and we do more and more work with the GPU. So if we're coming along and we're executing our x86 through whatever kind of translation layer, and now we have an interesting point in the history of computing here, where this, sure, a lot of work happens here, but a lot of the heavy lifting, a lot of the actual time-consuming work is actually something that's a GPU call. And it's less this x86 or ARM or whatever we have, and we're spending an awful lot of time offloading things to the GPU and taking those results and putting them back in here, or using this to render all of our, fancy 3D game graphics or whatever. So if they're able to make these GPU calls, basically keep those still as native, then we only have to translate this bit, and this can be, as we've already seen, quite efficient, and all of the real work is going to happen here in the GPU, and it's going to happen in OS functions. So really doesn't seem like anything surprising is happening here. This is something that we've been doing for a very long time in computing, and I have every level of confidence here that this will actually be quite fast. And when we want to talk specifically about x86 to ARM translation. And now keeping in mind that one of the very important things that we have here is that we've got macOS and macOS. We don't have to emulate or translate any of the operating system calls. We're like got two parallel worlds happening. And so this is one reason why this becomes all very easy, and particularly on Apple devices, we have known hardware. If you are on not Apple devices, if you're on a PC, the amount of hardware combinations, graphics cards and processors and instruction sets, it gets magnified a whole lot. But we start wondering, I wonder if anyone else has done this direct translation from one CPU architecture to another in the same operating system, and particularly with this x86 and ARM. And of course, that has already been done. Now, just in case you were not aware, it is in fact possible to run Windows on an ARM PC. Microsoft released their own devices that use ARM, and it is possible to install Windows on a Raspberry Pi, for example. And Microsoft provides emulation for x86 of the rich ecosystem of Win32 apps to be running on ARM PC. And they do this with the WAL64 layer that allows x86 code to run on the ARM64 version of Windows. This sounds really familiar to what we're already discussing. And a service caches the translated blocks of code to reduce the overhead of instruction translation and allow for optimization when the code runs again. And note that this was in fact now more than 2 years ago that this article was written. So we know that Apple has been working on this technology for a very long time. And we know that Microsoft has had technology almost exactly like this also for a very long time. So now if we think about this block of x86 code that needs to run before we do some OS call and some GPU offloading and whatever, and then this other x86 block that needs to call. Now, there's going to be something that's going to have to happen here. We're going to have to, probably translate registers. And then we're going to have to do things like manage the stack. And in general, deal with calling conventions. Because the calling conventions are different. The calling conventions, that is how we know that if we're going to, well, it's just about time for us to actually break out the Compiler Explorer now and actually discuss how this works. So of course, this being C++ Weekly, I would be remiss to not cover our Compiler Explorer code at least a little bit. Okay, so if I've got some sort of function call that takes an integer and returns an integer, and I'm just going to write my quick main function here. Like this, and I'm going to return a call to func that takes argc. This should be enough to demonstrate what we need to do here. So what we have is that this incoming parameter, argc, is being passed in the EDI register. And this function call func is expecting something in the EDI register. Main returns in the EAX register, and this function returns in the EAX register. So since these things match up basically perfectly, this gets optimized just crazy. We don't see the calling conventions come into a play at all. So let's just do a little bit of work here. I'm going to modify this by 2. So we can see a little bit. Let's put this in Intel assembly syntax here. And I'm going to take this one, have two parameters. And I'm going to do just a little bit of swapping around here. So I'm going to pass the value 3 here to the first parameter, and I'm going to pass argc to the second parameter, and now I'm going to multiply the result by 2. Now we get to see the difference between the x86 and the ARM instructions here. And I probably won't go over every single instruction, but push RAX, we're saving the value of RAX here. Move EDI into ESI. So that is taking this value argc, copying it into the register ESI, and now ESI becomes J, because the x86-64 calling conventions, in this particular case, are going to take this as the second parameter to the function. That's ESI. And then we move the value 3 into EDI, and that register, it becomes this I. So we took the thing that was EDI and moved it into ESI, so it's the second parameter, and we take this value 3 and we move it into EDI, and that becomes the first parameter. It's exactly what we're expecting here. Then we call our function, and the calling conventions know that the return value is an EAX, so we add EAX to EAX, and then that's going to be the return value from main, and then we pop our CX, so we're restoring this, returning from this function here. Okay. Now, I am using ARC64 on the right, and this is the assembly that the new Macs will be using, and I'm not quite as familiar with it, but we can trace through this. And if you've looked at any of my previous episodes on like learning assembly and learning how to read assembly, then most of this shouldn't be very surprising. We can see W0 is the argc value. We're going to move W0 into W1. So that becomes the second parameter. That becomes J. And then we're going to move 3 into W0. And when we move 3 into W0, that becomes I. So now we're passing 3 plus the second parameter into argc, into this function call. And then when the function call returns, we've got this W0. Now W0 is where the result comes back from the function call in the case of an integer. A logical shift left by 1 bit is the same thing as a multiply by 2. And then we do all the things to return from main here again. So you start to break this down, it doesn't look very complicated. And of course, I now have to take this to the next step, because I have personally implemented some code like this when I did my Commodore 64 presentation for CBPCon a few years ago. Now this is set up to show us the 32-bit Intel assembly, and then on the right here this is going to be 6502. So if I've got a main function, this program does nothing. Now unfortunately, I can't seem to zoom this at the moment. No matter what font I set it to, it doesn't zoom. So I'll zoom the whole UI a little bit, and it'll make things slightly unreadable, but it'll be better for the sake of readability in the video. Now, this thing is XORing out EAX. That's because main is going to return 0 by default and then return from main. Now I've got this here, I'm loading 0 into the LDA register on the 6502. I am storing this into some virtual memory locations that I had set up to represent these things, and then I'm going to return from subroutine. Now if I do the same thing here, now I'm not going to go nearly as complicated, but I'm going to create this function that expects an int and gets an int back. And I'm just going to call it like this. Now, this becomes very, in my opinion, realistic for what we're going to expect to see, or what the developers on this project would expect to see. So this is 32-bit, so it has to do a bunch of stack stuff, and it pushes the value onto the stack, and then that's this push L4, and then it's going to call get value, and then pull that value back off the stack, the return value here, and return from main. Now, my translator is doing something kind of similar. We're trying to set up this value, this ECX value, this push L instruction here, and then jump to subroutine of the get value, and then try to get these values back out off the stack and store them so that we can then return from the subroutine again. Now, what we end up with is code that you would never ever write on a 6502. It is not the efficient way to program here, but it is still native code that can execute, at least theoretically. Now, I know there's lots of problems here, at least theoretically, with efficiency. And this is the kind of translation you might see. You might see that in the code surrounding this operating system call on something like Rosetta, this might be, slower than optimal. Perhaps. But still really, really fast. And most of the slowness is going to have to come into the calling conventions, which I was just illustrating. So that's what's probably going to slow things down. And then they're also going to deal with this. Now, I said we would get back to this. Now, remember that the original Rosetta said it did everything except for G5. It could not do G5 instructions. So I have a bunch of unimplemented opcodes here in my 65 x86 translator. That's basically what they're talking about. They're saying, well, and this is again in the original Rosetta, that there's some instructions they couldn't translate. Now, we expect all software, all software for the x86 to run on ARM. So they're going to have to implement all of these instructions. It is entirely possible that for things that they, perhaps could not statically translate, and again, I'm making a lot of supposition about how they're actually doing these translations, but for the things that they could not statically translate, then they might have to revert perhaps to dynamic translation or emulation or something else. But they can probably still, worst case scenario, cache the results of the JITting process or the translation process. So the next time you go to launch the same application, it should be really, really fast. And again, by the time you're offloading so much of the work to the operating system and to the GPU and that kind of thing, you're probably not going to notice a difference at all in 99% of the case. Things that are truly heavily CPU bound, like compilation, perhaps. If you're trying to use your x86-64 compiler on your brand shiny new ARM Mac, that's probably a bad idea, because that's not a process that can be offloaded to a lot of operating system calls and to a lot of the GPU and that kind of thing. That's a better idea to use the natively compiled one. So yeah, there you have it. That's about everything that I know about this process. So I thank you for watching this episode of C++ Weekly. If you found this information interesting, please be sure to subscribe and give a thumbs up on the video.